Okay, now looking at the first part of number 2, we are looking at deriving the finite difference form of the heat diffusion equation for Cartesian coordinates with no generation and constant properties. So we can start by looking at the heat diffusion equation for the Cartesian coordinates that I derived in the first video. So that is C equal to the capacity times change in T over. Okay, so now when looking at this equation here, when we take out that there is constant thermal conductivity and no generation, we are then able to take out this term and pull out K and simplify it down quite a bit. So then we're going to be left with K equal to and so then this here is pretty much the simplest form of the heat diffusion equation. And so now that we have the simplest form, we can look at this right here, alpha, which is heat diffusivity, and this is equal to heat conductivity over density times heat capacity. And so then if you take a look at our simplest form right here, if you just do a little bit of rearranging, so if you divided by the density and heat capacity on this side, and then over here on this side as well, you can see that this and this matches up. So then we can plug in the heat diffusivity alpha into the equation and get I just rewrote that again. Divide over. Okay, and so then now looking at this equation, we can actually break each side down a little bit more. And so I will use some different colors here just to show talking about. So if we're looking at this side, we are going to be able to break that down into the temperature at a position J, and then to time N. So when we're looking at these terms, this temperature at a certain position J, and then at a certain time N. So first we're looking at a temperature at a later time minus a temperature at the same position at an earlier time, all over a change in position. And so that is looking at that side of the equation. And then if we take a look at this side of the equation right here, it's going to be simpler if we can break that down into alpha change partial derivative of x, and then partial derivative of t with respect to x. And so I'm going to now erase this work up here. And I just realized I made this change in position when it's supposed to be change in time. So now looking back over at the term in orange, we broke down this derivative again, and we are now going to be looking at approximating the second derivative from this. So the first thing that we're going to do is we're going to be looking at approximating the derivative at j plus 1 first. So that is going to be t at the position j plus 1 at time n minus temperature at j now, so different position but same time all over the change in x, the change in the position. And then also looking at the approximation of the derivative of just j, which is going to be t j at time n minus temperature at a position to the left at the same time all over change in position. And so then now that we have this, we can actually find the second derivative by subtracting these two, because these are basically just the approximation of the slope for j plus 1 and j. So by, I'm going to erase this down here now. So now by subtracting the two, so we can keep the alpha that I had and subtract the t j plus 1. And then putting all that over change in position. Okay, so basically you can then find your second derivative by the difference of the two slopes over the change in position. And so then all of this is going to be set equal to this, so I'll rewrite it back up over here. Erase this in here. And now you can look that we can pull some terms out, like both of the change in x terms. We could pull those out, and then we can add together some of the temperatures, and we could also multiply over the t and add over the tj at time n. And so we can do a lot of simplifying. So if we do that, then we're going to end up with the final equation of temperature at position j at time n plus 1 is equal to heat diffusivity, change in time, change in position squared, multiplied by temperature at n minus 2, temperature position j time n minus position. And this right here is your derived equation, and we call it finite because we're going to be using specific numbers to plug in. And so, oh, and then this term right here, that was really bad. That was wrong. This term right here is going to be really important, and it's just referred to as r, and this is essentially just a number. And we're going to be looking at that and plugging in different values for that quite a bit here in the next couple problems and videos. So, okay, and I just noticed looking back over my last video that I forgot to write in that I added the term tj to n on this side of the equation. So technically then it would be there we go. There we go. And that's the derived equation. Just forgot that one term.